Testing, testing, testing 1, 2, 3. Can you hear me? I hope this is working. This is Dr. Schultz here, and I'm so sorry I can't be with you today in AP Physics. So instead of actually being with you, I'm going to have my good-looking sketch here talk to you a little bit about a couple of very important examples that are related to magnetic induction. Now, what I'm going to ask the substitute teacher to do is to listen very carefully, because I'm going to be showing some slides, and I would like all of my students to be watching and listening. And after I've gone through a slide, I'm going to ask the substitute teacher to pause it so that all of you can write down what's on the slide. In other words, I don't want you to go madly writing things down while I'm talking, or you're going to miss the important stuff. Alright, do we think we can all do this? Here we go. The first example that I'd like to go through with you is the example of magnetic braking. Now, last week we talked about the slide wire generator, and we said that if you take a rod and you pull the rod at a constant velocity through a uniform magnetic field, and you allow that rod to be completing a closed loop, you'll generate an EMF around the loop. The example today is slightly different, and you have to be clear on what we're going to talk about now. In this case today, we're going to talk about the case in which the rod is given a push. In other words, it's given some initial velocity. We're going to call that velocity VI. And what will happen is that the magnetic force on the rod is going to exert a force on the rod in the opposite direction, which will gradually bring the rod to a stop. Okay? So it's very clear to understand that you need to understand in this case that nobody is pulling the rod in this problem. The rod was given an initial velocity, and it's allowed to be brought to a stop by the magnetic force. Now, this is an example of what we call magnetic braking, because obviously that magnetic force will be acting on the rod and will eventually bring it to a stop, and we would like to figure out an expression for the rod's instantaneous velocity. So we'll be solving for Vt. And we would expect the velocity to start at V initial and eventually go to 0. For the sake of the example, we're going to make the uniform magnetic field coming out of the page, just like we did before. And we will complete the circuit by introducing a resistor on the left-hand side. So I hope all of you can see that there is in fact going to be a closed loop on the left side of this picture. Okay. Now, I didn't draw it, but what I probably should have drawn was the fact that there's going to be a force acting on the rod. And I'm going to give you a moment to, after you copy this down, to draw that force acting to the left and to convince yourself that it's actually there. So you would want to draw a free body diagram for the rod. So substitute, please pause the slide and allow my students to copy down the information. Okay, so now let's solve for the instantaneous velocity of the rod. And again, students, I just want you to watch this, and then the sub is going to pause this slide after I'm done talking. So we always start off with something, right? And our assumption here is going to be Newton's second law. The sum of the forces is equal to mass times acceleration. And of course, we're writing that in differential form. Now, there's only one force that acts on the rod as it moves through the magnetic field. And I hope you sketch that force acting to the left on your free body diagram. That is the magnetic force. And it's the result of the rod moving to the right and dragging charges with it. And those charges are going to induce a current. And the current, of course, will feel a magnetic force that's equal to ILB. Now, we'll make ILB negative because of the direction. The magnetic force should be acting to the left, therefore we're going to be writing down negative ILB in this equation. And that's the only term to really worry about, is just negative ILB. There's no other force acting on the rod. Its initial velocity is not a force. That was simply the initial velocity. So there's only one term on the left side of Newton's second law. Now, the trick that we can play here is we can actually use our previous result from the slide wire generator, and we can substitute for the current in ILB. Okay, so take a look at what's written on the bottom half of the page here. Remember, last week we showed that the EMF induced in the slide wire is equal to B times L times V, where B is the external magnetic field, L is the length of the wire, and V is the instantaneous velocity. And the substitution that we make is that we realize this is a circuit, and so the EMF is simply equal to I times R by Ohm's law. And so you can substitute in and solve for I. So we end up with current being equal to B times L times V over R. And notice that as the wire slows down and has a smaller velocity, there will be less induced current, which should kind of make sense. So I'm going to ask the substitute to pause the slide, give you guys a chance to write, and then we'll finish this. Alright, and so what we have, of course, now is a differential equation. This is Newton's second law, written in differential form. We substitute for current. Okay, so we're substituting for I, BLV over R. And, of course, when we do that, we end up with an equation where on the right side you have, by the way, I switched sides here, so we have m dv dt on the left now is equal to negative b squared L squared V over R. Okay, and this is a pretty simple equation to solve. We can solve it by separation of variables. And so we get the velocity variables over on the left-hand side and the time variable on the right-hand side. So you can see that's why I switched sides earlier in the slide, because usually we put velocity on the left and time on the right. And when we solve this way, we set our initial conditions as initial velocity on the left side at time is equal to 0 on the right side. And we want to integrate to some time t and solve for an expression for v. So I'm writing these as definite integrals, and I'm integrating up to some expression v, and that would be my solution. So when we take the integral of 1 over v, of course that's the natural log, and I'll let you guys verify this particular result here. We've seen this many times. Of course the integral of t is very simple, it's just t. And when you exponentiate both sides, you end up with an expression for the instantaneous velocity, and it's equal to whatever the initial velocity is times an exponential decay function. And the argument to that exponential decay is b squared L squared over the mass of the rod times the resistance of the resistor in the circuit. And of course there's a negative sign there, and that gives us the idea that the velocity gradually approaches 0 as time goes on. And that result should make sense. So if you look at the graph here, the graph should make sense. We're starting with some initial velocity, and that initial velocity exponentially decays to 0 as time approaches infinity. So we've just solved this problem of magnetic braking. It's an interesting one, to consider. And the important point is that you can solve this by applying Newton's second law and separating variables. And again, the magnetic force is, acting on this rod, causing it to slow down. One other point that would be interesting, and I'll put this out as a question, would be what happens to the shape of this curve if you change the resistance in the circuit. And I'll give you a chance to think about this. If you were to make the resistance of the circuit very small, in other words, just make it extremely small so that the wire itself has very low resistance, what effect would that have on the curve shape itself, and why would that happen? I'm going to ask the sub to just pause the video just for a second before you write this down. I want you guys to talk about that. Okay, so sub, please just pause this, and then I'll tell you the answer. Okay? Okay, and I hope you've had a chance to think about that. The result is that if you decrease the resistance, the exponential decay will be quite a bit faster. Okay? And the reason would be that you're inducing a greater current in the circuit, and that greater current will cause a greater magnetic force to slow down the rod. And by decreasing the resistance, you're really allowing Lenz's law to induce more current to oppose this change in flux. Remember, as the rod is moving to the right, the flux through the loop is increasing. And if you decrease the resistance in that loop, you will allow the induced effect to be all the greater and to have a greater effect on slowing the rod. Okay, well that's the end of this example. I'll ask the sub to pause this slide so that you can write things down, and then we'll do one more example together.